This is a video on phase changes. This video is going to be kind of long, so after each different type of phase change, it's probably a good idea to stop. You've taken a sufficient amount of notes at that point, and just kind of like go back, take a look at your notes, think about it, and then of course move on if you would like at that point, if you want to move on to another phase change. If not, of course, then you can view the rest of this video on another day. And particularly, we're going to be looking at the phase change that occurs when a liquid becomes a gas and a gas becomes a liquid. It turns out that gases, in terms of the particles for which they make up the gas, have the least amount of order. Remember, gases are made up of particles which are very far apart, moving in rapid random motion. And if anybody could figure out how to stop this thing from coming up again, I would really appreciate it. Anyway, it seems to come up every time I do one of these videos. As we were saying, because gases are further apart, moving in rapid random motion, bouncing off of each other, bouncing off the walls of the container that they may exist in, gases have the least amount of order. And of course, solids, as you saw earlier, would have the greatest amount of order. These are solids down here, because they're arranged in a nice three-dimensional geometric repeating pattern, and that the particles in a solid are only allowed to really kind of vibrate through a fixed position. And so, least order, most order, liquids kind of in the middle, moving around, sliding over each other. Not a lot of space in between them, but still have much more, or a greater degree of freedom to move. So we're going to be looking at changes from the liquid to the gas phase and the gas to the liquid phase. When a liquid becomes a vapor or a gas, we call that evaporation. And when a gas goes back to its liquid state, we call that condensation. Now, I'm going to give you an explanation as to the process of evaporation. There really aren't any diagrams or any pictures or any drawings to go with this in this particular PowerPoint. But just listen, take notes, stop, write things down, rewind, re-listen if you have to. But get as much information as you can, and don't be afraid to ask questions in class when you come back the next day or the day after. During the process of evaporation, remember, the molecules in a liquid are moving around, sliding over each other, kind of colliding with each other, moving past each other. Not a lot of space in between them, but still they have certain degrees of freedom which are greater than those in which of a solid. So let's picture the molecules or the particles or whatever you want to call them at the surface of the liquid. So they're moving around, they're sliding around, they're banging into each other, and as they collide with each other, they transfer some kinetic energy from one molecule to the other, and we're going to assume that these collisions are elastic and no energy is lost during the collision as far as heat is concerned, but energy can be transferred from one particle to another. Well, in one of those collisions, if a molecule or sphere or particle, whatever you want to call it, has a sufficient amount of energy to overcome the intermolecular forces of attraction and is pointing in the right direction, it can literally leave the liquid phase and enter into the vapor state or become a gas. Now again, this is due to the fact that the molecules, as they're moving around, collide with each other, transfer kinetic energy from one molecule to another, and if a molecule at the surface gains a sufficient amount of kinetic energy that would allow it to overcome the intermolecular forces of attraction that are holding it into the liquid, it can overcome those forces of attraction and move into the vapor state. When a gas condenses, on the other hand, it is giving up energy, and so as it goes back down into the liquid state, it actually gives off energy, because the energy that it had as a gas now is lost as the intermolecular forces of attraction pull that molecule or sphere or particle in and hold it into the liquid. Over here to the left, you're going to see a couple of charts. It talks about the number of molecules versus the kinetic energy of the molecules. And this second chart shows you the same thing. This chart is related to the rate and ability of something to evaporate. This is our liquid at T1, and this is our liquid at T2. We see that most of the molecules under a temperature of T1 are over here and have about this much kinetic energy. We see in our other graph, T2, in which T2 is greater than T1, so this graph is for the liquid when it's at a higher temperature, the graph is flattened out more. Here at E1, this represents the energy, the minimum energy required for a molecule to leave the liquid state. I'm sorry about that, we'll go back. We see that at this lower temperature, there really aren't a lot of molecules that have the ability to leave the liquid state because they don't have a sufficient amount of kinetic energy to overcome the intermolecular forces of attraction. Remember, phase changes are very, very, very much dependent upon the strength of those intermolecular forces of attraction. And so at this lower temperature, since most of the molecules are over here, very few molecules have a sufficient amount of kinetic energy to leave the liquid state and go into the vapor state, and so we're not going to get a lot of evaporation. The evaporation is going to be much slower. Here at T2, where T2 is greater than T1, we're at a higher temperature, the molecules are distributed more, and this curve kind of flattens out, and there are more molecules with greater kinetic energy, and we can see that since E1 here represents the minimum amount of energy for a molecule in order to leave the liquid state, we can see that there are many more of those molecules here in this area which have a sufficient amount of energy to leave the liquid state and go into the vapor state. So we can see why, as the temperature of the liquid increases, the rate of its evaporation will also increase. Now, we're going to have a little discussion about evaporation. We'll go a little bit further. Again, there's not going to be really any pictures or any diagrams to show you some of the things that we're about to mention, but if you just follow along and listen well, and also stop and rewind and re-listen if you have to, do that too, so you can make sure that you get the information and understand it as best as you can, and of course ask questions tomorrow in class. So we start out with our liquid in our container. Let's say our liquid is water. The water in its container begins to evaporate to become a gas. The rate of that evaporation is pretty well constant. As long as we have water in the container, the rate of evaporation will pretty much stay constant throughout its existence within the container. Now, let's say we put a top on the container. So we've got this beaker of water, it's evaporating, and all of a sudden we come along and put a watch glass on top, which keeps the water from leaving. So the water can evaporate and go into the space above, but it can't go off into the rest of the atmosphere. What's going to happen is that water molecules begin to collect within that space. And of course, as they begin to collect, they actually begin to create a vapor pressure, a pressure due to the vapor that is above its liquid. So when something evaporates, when a liquid evaporates, when it becomes a gas, as it transfers into the gaseous state, like water evaporating in a puddle, the vapor above that liquid, the vapor of water above its own liquid, has a pressure like any other gas, and we call that the vapor pressure. as it begins to build up in our closed container, as the pressure builds up and as the amount of vapor builds up in our closed container, what happens is that the liquid, or excuse me, the gaseous particles begin to go back to the liquid state. We begin to get condensation. So our liquid water evaporates. It develops or puts gas up into the space above it. Vapor, water vapor. That water vapor has a pressure. That pressure is the vapor pressure of the gas above its liquid. As this gas begins to accumulate, the reverse process also begins to occur. And so as we get more and more water vapor, the water begins to go back to the liquid state. That rate of condensation starts out at 0 because there's very little water vapor above the liquid, and as more and more water vapor appears above the water, the rate of that continues to increase until that rate reaches the rate of evaporation. This double arrow is showing the process in which evaporation is occurring as it goes from liquid to gas, and condensation is occurring. The two arrows represent the opposite phenomena happening at the same time, and because they're the same length, they've now reached the same rate. And so the rate of evaporation and the rate of condensation have now become the same. When we have this situation in which the rate of evaporation and the rate of condensation are the same, we have what's called a dynamic equilibrium. A dynamic equilibrium is when two opposing processes are happening at the same time and at the same rate, like evaporation and condensation happening at the same time and at the same rate. Of course, as we had mentioned earlier, due to the evaporation, we have this water vapor in the space above it, and of course the water vapor has a pressure which we call the vapor pressure. And again, the vapor pressure is the pressure of the vapor above its liquid. When we have established an equilibrium, therefore, not only do we have the liquid water evaporating into the closed container, but we also have the gaseous water condensing back to the liquid. When that occurs at an equilibrium, right, we have a dynamic equilibrium, they're both happening at the same time at the same rate, the pressure of the vapor is known as the equilibrium vapor pressure. And as you can read, it's the pressure of the vapor measured when the dynamic equilibrium exists between condensation and evaporation. So we have a dynamic equilibrium when the rate of condensation equals the rate of evaporation. And we have a vapor above its liquid. That pressure, the pressure of that vapor above its liquid, is known as the equilibrium vapor pressure when the two are in equilibrium. This is an apparatus for measuring the vapor pressure of a liquid. We have the liquid, we have the container with the empty space above, and we have a manometer which is attached to it, and there's some mercury in here, and it's a little hard to see, but this represents mercury, and we can see the end of the mercury there and the end of the mercury there. So we place the liquid inside, and it begins to evaporate. And we can see here's a picture of the situation as evaporation is occurring. And the vapor now, remember, has a pressure, and the pressure is of the vapor, right? The vapor itself is pushing on the mercury in the tube, causing it to go upwards. The difference in the levels of the two represents the vapor pressure of the liquid as it is measured in millimeters of mercury. So this represents the vapor pressure of this particular substance under these conditions of temperature. Okay? If we're in equilibrium, then this measured distance in millimeters of mercury is the equilibrium vapor pressure. If we're not in equilibrium, then what we measure here is just the vapor pressure. If we are at equilibrium and the rate of condensation and the rate of evaporation are the same, which appears that it probably is, since we have two molecules coming out of the liquid and we have two molecules going into the liquid, we would assume that this pressure is the equilibrium vapor pressure. So this represents what happens before and how we measure the pressure before evaporation. And again, there is no pressure because there's no evaporation yet. And this is what happens at equilibrium, in which now we have the rate of the condensation and the rate of the evaporation being equal to each other. Now, let's talk about an enthalpy change that occurs when a liquid boils. The enthalpy change that we're going to talk about is known as the molar heat of vaporization, and it's given the symbol delta H vap, or delta H vaporization. It's the energy required to vaporize 1 mole of a liquid at its boiling point. Why is this information significant? Well, it gives us some information about the strength of the intermolecular forces of attraction. The stronger the intermolecular forces of attraction are for a liquid, the greater the molar heat of vaporization is going to be. We're going to take a look at this graph over here, and this is a graph of vapor pressure in atmospheres versus temperature for 3 different substances: diethyl ether, water, and mercury. 1 atmosphere is particularly shown on this graph, and it's shown on this graph with this dotted line because of the fact that we live in a condition in which we are under 1 atmosphere of pressure, pretty much for the most part. We know it changes from day to day, but for all intents and purposes we are under 1 atmosphere of pressure. Notice the line at 1 atmosphere of pressure goes down, and what's the temperature? That's the boiling point of water, 100 degrees Celsius. Apparently there's a relationship between pressure and temperature, and we'll talk about that in a little while, in terms of boiling point, that is. Well, if we look at the curve for each of these substances, and they kind of look the same, although they're a little bit different. They kind of look the same. Diethyl ether is lower, water's in the middle, mercury's here. There's more of a curve to the mercury one, and the curve on the diethyl ether and the water look pretty much the same. But what it's basically telling us is that there's a relationship between vapor pressure and temperature. And it's not a straight line. It's a curve. And curves, well, you know, I mean, they tell us something, but it's always easier for us to learn more about a phenomenon if the relationship is a linear one. And so, 2 men simultaneously, by the names of Clausius and Clapeyron, decided to try to do something about that. And what they determined is that we can get a linear relationship if we took the natural log of the vapor pressure, where P is equal to the equilibrium vapor pressure, and plotted it versus 1 over T, where the temperature T is in Kelvin. And of course R is the ideal gas law constant, and it is the value 8.314 joules per Kelvin mole, not the value 0.0821. And so this is a linear equation where the ln of P, the natural log of P, is our y, 1 over T is our x, the slope of the line should be negative delta H vaporization over R, and C is the y-intercept. And so let's make a plot of log of P, natural log of P versus 1 over T for 2 of those substances. This one being water, obviously, as you can see, and this one is the diethyl ether. Okay, so instead of writing out the name, they give you the formula. So this one here, as you can see the arrow pointing to, that's the diethyl ether. We can see that the natural log of P versus 1 over T makes a nice straight line with a negative slope. And of course the negative slope is equal to delta H of vaporization over R. So the slope of these lines for these 2 curves for those individual substances is negative delta H vaporization over R. If we were to multiply the slope of these lines by the value of R, we would get the delta H of vaporization. And of course, the greater the delta H of vaporization, the more energy it takes to vaporize 1 mole of a liquid at its boiling point, the stronger its intermolecular forces of attraction are. Now, the Clausius-Clapeyron equation, as you saw in the last slide, is very useful in looking at the relationship, developing a linear relationship between the log of P and 1 over T, the natural log of P and 1 over T. It's useful for determining the delta H of vaporization, for which the delta H of vaporization for most liquids was determined using that method. But it's not really all that useful for solving problems. And so we're going to do a very quick derivation of an equation that is based upon the Clausius and Clapeyron equation. We write the equation in terms of T1 and P1. That is, this is the temperature of the system, we're going to call T1, and this is the vapor pressure of the liquid corresponding to a temperature of T1. Now, we're going to change that temperature to T2, and it could be less or it could be more. It really doesn't matter. It could be greater than T1 or less than T1, It really doesn't matter. And this is the corresponding vapor pressure associated with that particular temperature. And of course, those temperatures are in Kelvin. Now, if we take those two equations and divide one equation by the other, without going through the math, we end up with an equation that looks like this. And it tells us that the natural log of the ratio of P1 over P2 is equal to the delta H of vaporization over R times T1 minus T2 divided by T1 times T2. And this equation is a very useful equation. There are problems in the text that will use this equation, and there are also at least one problem in the packet that I gave you that is also going to use this equation. So when you get to it, you should know. If you don't, you know where I am, or you know where your classmates are. Let's talk about boiling, okay? Because again, we're still talking about the transition of a liquid to a gas, or a gas back to a liquid. Let's talk about boiling. Boiling is something you're all familiar with. You've seen water boil. You may have had an opportunity to cook some food at home. Maybe you made some macaroni and cheese and you boiled up some water to do that. Or maybe you like hot tea and you boiled up some water for hot tea. Most of the time we think that boiling is a heat phenomenon. It's a phenomenon that is definitely, you need to heat something in order to get it to boil. Well, I'm telling you right now it's a misconception, because boiling is really a pressure phenomenon. Boiling occurs, my friends, when the vapor pressure of the liquid is equal to the external pressure. That's when the bubbles that form at the bottom can now reach the surface, because their pressure is equivalent to the pressure above. The boiling point, as we can see, is the temperature at which the equilibrium vapor pressure of the liquid is equal to the external pressure. So the reason we have to raise the temperature of water to 100 degrees is because water's vapor pressure is pretty low. It has a fairly low vapor pressure because it has strong intermolecular forces of attraction. If it had weak intermolecular forces of attraction, then its vapor pressure would be higher. Anything with weaker intermolecular forces of attraction has higher let's try that again. Anything with weaker intermolecular forces of attraction are going to have lower boiling points, and anything with stronger intermolecular forces of attraction are going to have higher boiling points, because those molecules are held together more strongly, and it's going to take more energy to overcome the intermolecular forces of attraction. So you've got to heat it to a higher temperature in order to get the boiling point, in order to get the vapor pressure up. So water will begin to boil at 100 degrees Celsius because that's the temperature at which its vapor pressure becomes equal to that of the external pressure, which is 1 atmosphere of pressure. If the pressure is higher than 1 atmosphere of pressure, then the boiling point of water will be greater than 100. If the pressure is less than 1 atmosphere of pressure, then the boiling point of water becomes less than 100 degrees Celsius. We can see by looking at both its boiling point and its delta H of vaporization that water has very strong intermolecular forces of attraction. Looking at methane, its boiling point is very low, its heat of vaporization is not very large, And that also is an indication that it has weak intermolecular forces of attraction. Strong intermolecular forces of attraction, as indicated by a high boiling point and a large delta H of vaporization. Weak intermolecular forces of attraction, as shown by a low boiling point and a small delta H of vaporization. And again, boiling is really a pressure phenomenon. Something boils when its vapor pressure is equal to that of the external pressure. And that occurs at the boiling point, which is the point at which the equilibrium vapor pressure becomes equal to the external pressure. The normal boiling point is the boiling point when the pressure external is at 1 atmosphere. As we were mentioning before, we know that water boils at 100 degrees Celsius, but that occurs at 1 atmosphere of pressure, and that's the normal boiling point. Above 100 degrees Celsius, the water would boil at a temperature above 100 degrees Celsius if the pressure was greater than 1 atmosphere. And it would boil at a temperature lower than 100 degrees Celsius if the pressure was less than 1 atmosphere. Critical temperature is the temperature above which the gas cannot be made to liquefy, no matter how great the applied pressure is. If you have a gas and you squeeze it, compress it, add pressure to it, you can get the gas to liquefy. But it is dependent upon the temperature. The critical temperature is really the highest temperature at which you can apply pressure to the gas to get it to liquefy. The reason is that at this temperature, the relationship between the intermolecular forces of attraction and the temperature is significant. No matter how much you squeeze this, at this temperature, above this temperature, no matter how much pressure you apply above this temperature, above this temperature, you cannot get it to condense because the intermolecular forces of attraction are not strong enough to overcome the amount of kinetic energy that the particles have. So the critical temperature is the temperature at which above this you cannot liquefy the gas. No matter how much pressure you apply, if the temperature of the vapor is above it, it will not liquefy because no matter how much you squeeze it, no matter how far you push them close enough together, the intermolecular forces of attraction are not strong enough to overcome the amount of kinetic energy that the particles have. At the critical temperature, there is a specific amount of pressure that can be applied minimally. This is the minimum amount necessary at the critical temperature, and we call that the critical pressure. The critical pressure is the minimum pressure that must be applied to bring about the liquefaction at the critical temperature. So again, if the vapor is at the critical temperature, it can still be liquefied by applying pressure to it, but the minimum amount of pressure is called the critical pressure. When it's above that temperature, when the temperature of the vapor is above that temperature, the critical temperature, no matter how much pressure you apply, you cannot get it to liquefy. And that's because of the fact that even though you may push those molecules closer together by increasing the pressure, no matter how close you can push those molecules together, the intermolecular forces of attraction are not strong enough to overcome the kinetic energy that those molecules have. Here's an example of the critical phenomenon for the substance SF6. Over to your left, we have some SF6, and whoops, wrong button. Oh, let's try this again. And as we were trying to tell you, the temperature is less than the critical temperature, and it's all liquid. Here in the next picture, the temperature is above the critical temperature, and we can see no liquid exists. Here, when we go over to the next one, the temperature is about equal to the critical temperature, and now we can see we're beginning to get some liquid vaporizing, or some liquid forming. With some of the vapor is beginning to condense. We can see some of the liquid, and we can also see some of the liquid that's forming that's kind of like suspended by the vapor. And then last but not least, here the temperature is below the critical temperature, and we can see that we're going all to liquid. So there's a sufficient amount of pressure in this tube to liquefy it. There isn't a sufficient amount of pressure in this tube to liquefy it. Oh. Phase changes. We're going to look at a different kind of phase change now. So if you wanted to stop the video and take a break, look at your notes, digest, fine. Do that. If you want to keep going, keep going. Let's look at the phase change that occurs between solids and liquids. Of course, when a solid becomes a liquid, it's melting. And of course, when a liquid becomes a solid, it's freezing. And of course, it is possible to establish an equilibrium between solid water and liquid water. When solid water melts and liquid water freezes, if these two phenomena are happening at the same time and at the same rate, we will have a dynamic equilibrium, as shown by the double arrow here. The melting point of a solid, or the freezing point of a liquid, is the temperature at which the solid and liquid phases coexist in equilibrium. The melting point and the freezing point turn out to be the same value. The solid will melt at the same temperature that the liquid freezes. If the two are held together at the same temperature, we can establish an equilibrium between the two. Once we increase the temperature above that, it will favor the forward process and it will melt. Or if we lower the temperature below the freezing or melting point, then it'll favor the reverse process and it'll freeze. And that's generally what we're used to. We're used to either the temperature being above 0 degrees for water or the temperature being below 0 degrees for water. And we would either see above 0 degrees, we're going to see it melt, and below 0 degrees, we're going to see it freeze. If we establish both of these at 0 degrees Celsius, what we would see is an equilibrium. Kind of like slush. You know how like a puddle of slush is kind of icy and liquidy all at the same time? And it just kind of like sits there, and you know, maybe it gets really, really cold and then it freezes, or maybe it gets really, really warm and then it melts. But on those days in which it's pretty much just slush, that's because we're at 0 degrees Celsius, 32 degrees Fahrenheit, and we've established an equilibrium between the two. When it comes to melting and freezing, like a delta H of vaporization, when it comes to boiling and condensing, there's a molar heat of fusion, or a delta H of fusion, and it's the energy required to melt 1 mole of solid substance at its freezing point. Here are the melting points, and here are the delta H of fusions in kilojoules per mole for a variety of different substances. And of course, the melting point of water, as you know, is 0. And it has a relatively high delta H of fusion, not like mercury, but relatively high. Melting point and delta H of fusion are also measures of the strength of the intermolecular forces of attraction. Generally, the higher the melting point is, and the stronger the intermolecular forces of attraction will be. And also the same thing is true for the delta H of fusion. The higher the delta H of fusion is, the higher the heat of fusion is, the stronger the intermolecular forces of attraction are. This is a heating curve that basically takes us through several steps, in which we start out with a solid at a given temperature, and as we warm up the solid over time, we see that the temperature rises. When we get to this point, we see that even though we continue to heat the object, whatever it is, and time passes, the temperature does not change. This is the point over which we have a solid and liquid equilibrium occurring. This is the point at which we begin to melt the solid. As we heat the solid and we continue to heat solid, as it melts, the energy that you're putting into it goes into overcoming the intermolecular forces of attraction and melting it. It does not go into increasing the average kinetic energy, which would cause the temperature to increase. Here, when it's still a solid, you're heating it and what we're doing is increasing the average kinetic energy, and that's why the temperature goes up. Here, we're trying to overcome the intermolecular forces of attraction. And so the temperature is not going up, and it continues to continue over time. The temperature doesn't change, but we keep adding heat, and it melts. When we get to this point right here, now we've got it all melted, and now it's a liquid, and we continue to heat it, and as time goes by, again, because it's all one phase now, but it's not an equilibrium between the liquid and the solid, it's just a liquid right now. As we heat it, the energy that we add to it goes into raising the average kinetic energy, and therefore the temperature goes up. Once we get to the boiling point, we continue to heat this, and now we establish the liquid and vapor equilibrium. And so again, the energy is going into overcoming the intermolecular forces of attraction, not going into the raising the average kinetic energy, which of course would cause the temperature to go up. So the temperature stays constant because the energy is not going into raising the average kinetic energy, and it boils until all of it boils. And now we are in the vapor state. We are no longer in that liquid and vapor equilibrium, and if we continue to heat it, the vapor will continue to rise in temperature. Now, in order to find Q for each of these various points along this curve, when the curve is going upwards and the temperature is changing, like from here to A, and from B to C, and from D to wherever, the equation to find the amount of heat involved is equal to M times S times delta T. Here, when we get to this point right here and this point right here, these two lines between A and B and between C and D, since the temperature is not changing, we cannot use MS delta T. What we can use, though, is the number of moles of the particular substance, whatever that substance is, let's say it's water, multiplied times its heat of fusion. The number of moles of that substance times its heat of fusion will give us the value of Q, for this process. And same thing is true here, only since it's boiling and we won't use the heat of fusion, we're going to use the heat of vaporization. So if we knew the number of moles of this substance, well, let's say water, if we knew the number of moles of water that we were boiling, and we knew the heat of vaporization of water, which is about 6 kilojoules, I'm sorry, it's greater than 6. If we knew the heat of vaporization for water, we can take the number of moles of water, multiply it times the heat of vaporization for water, and we can find out how much energy, how much heat the water absorbs during the process. And of course the same thing is true for the reverse process, but instead of energy being added to the system, energy is being removed from the system. So we can find how much energy is released as it cools down and begins to liquefy using MS delta T. We can find out how much energy is released as it condenses using the number of moles times the heat of vaporization. We can find out how much energy is released as it cools down from 100 degrees Celsius down to 0 degrees Celsius, and that again is MS delta T. We can see how much energy is released as it freezes, and that's N, the number of moles times the heat of fusion. And of course we can use MS delta T again here. Now S for a solid, S for a liquid, and S for a vapor, and again S is the specific heat. Those values are different, and you can find those in your book. Phase changes. Sublimation, the formation of a gas directly from a solid. The formation of a solid directly from a gas. Deposition. Sublimation, deposition, deposition being the opposite of sublimation. It is possible to establish a dynamic equilibrium between the two. The molar heat of sublimation is the energy required to sublime 1 mole of a solid. It turns out that the molar heat of sublimation is equal to the heat of fusion plus the heat of vaporization, which only makes sense because this would represent the delta H of fusion, the molar heat of fusion, and this represents the molar heat of vaporization, and this arrow plus this arrow is going to be equal to this arrow. And it is, of course, established through Hess's law. And that's it with phase changes. I never thought we would get rid of through that, but we did. All right, my friends, watch it, learn it, watch it, stop it, review it, rewind it, ask questions, and we'll see you tomorrow in class. Damn, you didn't finish recording it, did you? Oh, goodness gracious. How far did we get? No, I'm not trashing.